Hello students, welcome back. In section 1 we studied classical examples of cryptography along with some history. Now let's go to section 2 and study modern cryptography. Let's work out some crypto systems that are actually in use currently. As a matter of fact, just one system. RSA Encryption, Diffie and Hellman, 1976. 1976. It's very new in mathematical standard. Can you think of any other example in mathematics that are this new? I mean, as new as 1906, let alone 76. Anything in algebra or analysis or statistics anywhere? Geometry anywhere? Yeah, I didn't think so. This is really new. The reason we can do such a new discovery, such a new system here in undergraduate level is because this is part mathematics, part computer science. That's why. Mathematics is really classical field, but computer science is not. It's the opposite. And of course, in this course, we are going to approach only in mathematical viewpoint. But remember, there is computational aspect on it. RSA encryption is a public key crypto system. The encryption key, which consists of two numbers, N and E, is publicly released. So anyone who wants to find out can find out. But it is made through an interesting process like this. We begin from a couple of large primes, kind of like 30-digit number and 40-digit number, those kind of things. And then multiply those two to get N, which is part of the encryption key. And then another positive integer, which is relatively prime to P minus 1 times Q minus 1. And put those two together and we have the encryption key. And after that, P and Q are discarded. Oh, as a matter of fact, no. After that, P and Q will be used to create decryption key as well, and that has to be kept hidden. And then encryption key is publicly released, and then P and Q are discarded so that nobody can backtrace and break anything. So, getting P and Q, which are really humongous primes, with encryption keys and decryption key is next to impossible. I mean, within reasonable time frame, within kind of lifetime of the universe, that's not possible. So many people call it zero-point encryption or things like that. Zero-knowledge encryption, zero-knowledge crypto system, because nobody knows, including the computer. Really nobody knows. By the way, why P minus 1 times Q minus 1? Well, that's because of this. It's phi of n. Remember phi? Euler-Tojan function. It is multiplicative. So phi of n is phi of pq. And therefore it is phi of p times phi of q. And that's how we get P minus 1 times Q minus 1. So this condition here, which I just highlighted in purple, is equivalent to this one here. Same color. Phi of n and E are relatively prime. And of course, you don't really have to bother this one if you select E as a prime number, and there are a lot of prime numbers out there. And their mechanism to find or cook up some big prime numbers, and computers use those kind of things to get P and Q and then destroy. Likewise, computers can find good E value as well. Okay, that's a preparation. And then here's one more preparation. RSA encryption employs a block cipher system, so it decomposes the original text, capital M, to equally sized blocks, M1, M2, M3, and so on. Kind of like this. And if the last block lacks some characters, you can put anything in there, any meaningless stuff in there, and then create some block, the final block. Finally, in each block, apply the encryption function, which is m to the e power. Now maybe some students will recognize that, oh, that's why e is selected as relatively prime to phi of n now, because this is mod n. And then if you apply those the exponent rule and multiply another m to the another power, then we have addition among the powers, and m to the e power to some other power, then we have multiplication of the powers, and they're all modulo phi of n, and that's why we have that. And if you're a little bit hazy about that, go back to lesson 12 and study that part, the primitive root and those kind of things. That's where we discuss those. Here, we are not going to go that deep back again. Just keep those as kind of mechanism, kind of step process, and just follow that. Let's go to an example problem. Let's do an encryption problem now, and we're going to study the decryption in a separate video. Here we go. P is 43 and Q is 59. They're both prime, and then N is P times Q, which is 2537. And then public key is 2537, comma 13. And please recall, 13 is a prime number, so I don't really have to bother with the GCD condition here. Prime number is relatively prime to everything, but I did it anyway. And then encrypt the message stop. Okay, all right, let's do that. First, let's write stop in terms of digit string. A is 00, B is 01, all the way up to Z, 25. According to that, STOP can be written as follows: 18, 19, 14, and 15. All right? Okay, next, decide upon the length of the block. How do you do that? Well, we use this trick, and the reason is, that's a long story, but I'm not going to talk about it. We use the criterion of 25. 25, and certainly bigger than that. 25, 25, bigger than that one too. 25, 25, 25, okay, it's less. Somewhere in between, we'll go with this one, and we take 4 digits. And what if it's bigger than this? Then we go with another 25. 25, 25, 25, 25. And then more 25, and then another 25, you see. And so depending upon how large your n is, you're going to get either 4-digit or 6-digit or 8-digit, and so on and so forth. In this particular case, 4 digits. So we have 2 4-digit numbers, 18, 19, and 14, 15. All right, finally, apply the encryption function. 18, 19 to the 13th power modulo n, and 14, 15 to the 13th power modulo n. You can do this computation as we have here. So the conclusion is 2081, 2182, as you see here. That's the encrypted message of stop. Please note that we only used N and E. We never used P and Q in any of this. So after creating the keys, P and Q will be discarded. Okay, that's how we do RSA encryption. And as for the decryption, we'll talk about it in a separate video a bit later.